Hi, this is Mrs. Vrobel. This is part one of States of Matter. So up to this point, we've talked about stoichiometry, which is looking at the relationship between reactants and products, and we've looked at the moles with counting particles. So now we're going to go back to matter and see how do the different states of matter interact with one another or with themselves. By the end of this video, you will correctly use the kinetic-molecular theory to help explain the behavior of gases, and you will accurately describe how mass affects the rate of diffusion and effusion. Okay, so we're going to talk about kinetic behavior of gases, and I have a balloon here. And as I blow up the balloon, I want you to think about what is happening to the air as it goes into the balloon. So somehow the gas from my lungs is traveling through my mouth into the balloon. And what's happening to those air particles as it does that? So please note that all gases are composed of tiny particles called molecules. These molecules are in a constant motion, so they don't stop. On average, the molecules are very far apart. I like to say they're sort of like your relatives that can't stand each other. They like to occupy different corners of the room. And please note, as temperature cools down, velocities decrease. So the average kinetic energy of a molecule decreases. Now you might notice that. Think about what happens if you get a helium balloon at the grocery store or the party store, and you go outside in the wintertime with the balloon. What do you think happens to the balloon? We'll talk about that in class. Okay, another part of the kinetic molecular theory is molecules are perfectly elastic. So we assume that when gas particles collide, they don't lose any of their energy. Now this is the last thing that we're assuming. You could treat the gas particles like billiard balls where they knock each other and they retain their energy, but in reality, we actually do have attractive forces that are between those molecules. Sometimes they stick together briefly, and sometimes they lose their energy. Okay, so think about that balloon that I filled up with my air. The question is, why do gases expand until they fill the container? How come gases are compressible where liquids aren't? And this is another good question, and this leads into the next topic that we're going to talk about. How do odors make their way across a room? So if you have somebody entering in the room that obviously has a lot of cologne on, how does that scent travel to you? Okay, think about this. Gases easily flow past each other, and the reason why is most of the time they are not attracted to each other. So they typically are not as attracted. Therefore, because of that, they easily flow past each other. Now, diffusion. This is where we look at perfume or cologne. It's the movement of one material through another. So the air particles, they are actually mixing with the scent or the cologne that somebody is wearing. So that person has that odor that is transferring through the air to your nostrils, and that's what we call diffusion. Now, what is diffusion? It's essentially the gas escaping through a balloon or maybe a tire that has a nail in it. So essentially, it's a restricted opening and the gas is traveling through that opening. Now we're going to learn a new problem called Graham's law of effusion. You may hear diffusion. It's a very similar concept. But anyways, what it means is that the rate of effusion is approximately 1 over the square root of molar mass. So this is a formula that you're going to need to know. This is not something that I'm going to give you on the quiz. Now here is the typical formula. Now notice that rate A is diagonally across to the molar mass of the gas. So if we're comparing oxygen to nitrogen, oxygen, its rate is going to be on top. So O2 would be over here. Its molar mass is going to be down here. And then nitrogen, its rate would be over here, but its molar mass would be over here. And notice it's N2 and O2, so that means you have to add up the molar mass of 2 oxygen and 2 nitrogen. Now here's a problem, and I want you to write this down because we're going to go over it in class. Ammonia has a molar mass of 17 grams per mole, and hydrogen chloride has a molar mass of 36.5. So they want the rate of diffusion. So I'm going to do the rate of ammonia, so RNH3, divided by the rate of HCl. And then I'm going to do a big square root. And hydrochloric acid has a molar mass of 36.5. So notice I'm doing it diagonally from its rate, divided by 17 grams for molar mass of NH3. All right, so I want you to do that calculation and bring it into class, and we will double check our answers. Okay, so the summary for this video is that gases expand, diffuse, they exert pressure because they're in a low density state, and they have tiny, constantly moving particles. So I'm blowing into this balloon, and as I blow into the balloon, notice that the air that I put through my mouth is expanding the balloon itself, okay? And I'm getting pressure as a result of it. And then lastly, we have Graham's law. In Graham's law, we're going to look at diffusion rates of 2 different gases. You might notice that the heavier gases are going to have a slower rate of diffusion based on that.